So here are some comments I'd like to make about these. The first is that there are a whole bunch of steps involved in doing these surface integrals, and so you need some practice and you need to be aware of what all the steps are involved so you don't accidentally mix something up partway through. And just like with arc length integrals, these are extremely sensitive to small errors. If you make a slight mistake in the arithmetic partway through, it can really mess you up. So be careful with these types of surface area calculations. And third, because there are so many moving parts to this individual calculation, having formulas in your pocket that work in special cases can save you a whole lot of work. So just to iterate what the steps are in doing this calculation, step one is always going to be find a parameterization. That's always what we got to start with whenever we're doing a calculation in multivariate. The second thing is we have to calculate what are the tangent vectors? What are the tangent vectors in the first direction and the second direction? Then we got to take their cross product, and then we got to find its length, and then we got to integrate that sucker up using a double integral. So here's an example of a special case. So when we had a triangle or a parallelogram, we always had a parameterization that said phi of st is a start point plus s times a first direction vector plus t times a second direction vector. So here I've used s and t instead of u and v as parameters, but that's okay. I still just calculate two tangent vectors, the tangent vector in the s direction and the tangent vector in the t direction. Those give me back my direction vectors, v and w. And so in this case, the area distortion factor is constant. It's just the length of the cross product, v cross w. So that's one way that you could go back and recover the formula for the area of a triangle or a parallelogram. If we've got the graph of a function, the graph of a function is another special case that's extremely handy. So if we've got a graph like this, z is equal to g of xy, where g is some function of two variables, then we can use this particular parameterization where we solve for one variable in terms of the other two. And then the calculations of the tangent vectors, tu and tv, are pretty straightforward because the derivatives of our first two functions, u and v, are pretty simple. And our cross product has this formula. It's minus del g del u minus del g del v, comma 1. And so when we feed that into our length calculation, the length here is the square root of 1 plus the first partial derivative squared plus the second partial derivative squared. So this formula here is worth remembering because it greatly simplifies everything that goes into this surface area calculation when we have the graph of a function. So for example, let's talk about finding the surface area of the graph of z is equal to xy over the circular sector, where x is greater than or equal to 0, y is greater than or equal to 0, and x squared plus y squared is less than or equal to 1. So that's the part of the unit circle where x and y are both positive. It lies between angle 0 and angle pi over 2 in polar coordinates. So our function now, g of uv, we're looking at the graph of the function u times v, like so. And so to calculate this, we're just calculating the double integral of 1 plus the derivative of g with respect to u squared plus the derivative of g with respect to v squared du dv over this region. And in this case, it's handy to switch to polar coordinates. It's handy to switch to polar coordinates from u and v coordinates because our region is nicely described in terms of polar coordinates. And the thing we're integrating involves a u squared plus v squared. That's just going to turn into r squared. So let's do a change of variables to polar coordinates. To change to polar coordinates, this turns into the double integral of the square root of 1 plus r squared times r dr d theta. Our radius goes from 0 to 1, and our theta coordinate goes from 0 to, like we were saying, pi over 2. And now, this integral is doable on the inside because we can do a substitution. We can substitute w is equal to 1 plus r squared, and then dw is equal to 2r dr. This becomes an integral from 0 to pi over 2 of an integral. If w is equal to 1 plus r squared, then this is going to turn into an integral from 1 to 2 of the square root of w times dw over 2 times d theta. And so we can then kind of finish out this calculation if you like. But the total surface area is calculable. These are the steps, and you can see how normally doing the tangent vector calculation would be a lot of work. Here we get the thing we're supposed to be integrating almost right away by having this formula in our pocket.